most of the material that is presented here today is listed and actually printed on your lecture notes that's associated with this. I actually call them course notes rather than lecture notes. And for this particular topic that I'm going to go over today, make sure to refer to both your textbook and the course notes for basic electrical measurement and sensing. So I'm going to briefly, again, we are trying to cover the basics, the electrical measurement and sensing devices, and there are so many of them to be covered. There are actually courses exclusively dedicated to those, but we are trying to concentrate on the basics. As such, we are really looking at some of the basic topics. So advanced topics, we leave it for other courses. So as you know, you may know, or you should know, if you've already taken a circuit analysis class, there are two types of current that we are dealing with in circuits. One is DC, the other one is AC, the direct current and the alternating current. The wave of a DC current is shown as such here in this particular figure. The power is, if we have a resistor, if we have any kind of a resistance, then the power would be proportion to the resistance and the square of the intensity. And if we change the situation a little bit to a DC, from DC to AC current, and then if we have AC current with pretty much if we have a current that is flowing through a resistor, and the current itself, for an AC, the intensity function I versus T is given here. The current versus T is given here. So if you have a current that varies over time, okay, and let's say in this case it goes from minus 5 amp to plus 5 over a certain time, and the period is shown as such, from this point to this point, that would be the period of such a wavelength, such a wave. So as such, up here it's going to be 2t and 2t, and as such, it's going to give us this pattern that you can see here. Usually I sub t is I sine 2 pi t divided by the capital T, by period, in which capital T is the period. So if we have a current of interest that is flowing through a resistor, and I sub t is shown as such, in this case the power that will be dissipated by the resistor itself at each point in time, or at each instant in time, it's going to be given, the power dissipation will be given by this equation that's shown here. P is R I sub t squared. Okay, and as such, if we would like to pretty much calculate the average power, we need to use some kind of a statistical method. In this case, we use a root mean squared, RMS, the currents. Don't worry too much about RMS. It's pretty straightforward, but you need to know that how we can actually apply RMS. So the current I sub RMS would be given by this function that you see here. Okay, and basically, in order to calculate the I sub RMS, we would take the integral of the function at time t, and from 0 to t divided by a period, take the square root of that, and that would pretty much give us I sub r m s, as you can see here. So from there, we can also calculate the P sub AV, which is the average power dissipated in a resistor when the current flows. So we can also do that again, and they're pretty straightforward the way we apply it for this class. So let's take a look at some of the meters that are some of the analog meters that are used in electrical measurement devices, in electrical devices and measuring devices. The NBIL is a famous one. N is the number of turns of the coil. I, L, and N is defined previously. Well, BI and L is defined previously in previous lectures, but they're basically nothing. There's no magic about them. And the formula for F, again, B times I times L. This is not sub, but it is actually the equation itself. Can't edit it now because I use an equation editor to do this, and I don't have access to it right now. But anyways, BIL, as it was defined previously in previous lectures, B is the magnetic flux, I is the electric current, and L is the conductor. So BIL or LIB, some people like to use that because it's easier to remember the formula. The conductor length is L, I is the electrical current, and B is the magnetic flux density expressed in Weber per square meter. So going down here to going back to our formula under discussion, F could be pretty much calculated as such, knowing the number of turns of the coil. There are also additional references that are provided here. That is in Wikipedia. I found that particular topic to be pretty credible. The electrodynamometer is another AC ammeter or a meter based on magnetic solenoid motion of an iron plunger in a fixed conductor coil. They're only effective for low, pretty much low frequency AC. Remember, this lecture notes that I'm going over with is pretty much a shorter version, so it's more like a summary of what you need to know for this class. So it is only effective for low frequency AC currents, otherwise they're not very effective. Then there's a thermocouple meter. This is an AC ammeter, and the intensity is translated into heat, and then we measure the temperature by a thermocouple. It can read both. Let me also add this here. It can read AC currents up to 100 megahertz of frequency. So the higher frequency could also be read by thermocouple meter. Then there's a voltmeter. You probably used that many times. I've seen it. It's a typical device that we measure. V is IR. An additional resistance can be positioned in series with an ammeter to proportion the electric current to an electric potential. The analog versus digital signals are also stated here. Again, you can read much of this on your own. Really no magic to them. The way that we actually measure and the way it is formed, the typical measurement input circuit, it is formed as such. And you can see here the measured signal. You can read this from horizontal figure that I provided from left to right, or you can read it from pretty much top to bottom. I prefer the top to bottom explanation here. The measured physical property, it's going to go through a transducer. It's going to be converted to an electric signal. From there, it's going to go to an input circuit. And of course, throughout this process, there are many different functions that would be performed, many different type of perhaps maybe we should call it transition. They would go through different types of transformation. That's a better word in this case, and eventually, after it's been processed, it will be shown on the display for a particular device. Okay. I would like to go over an example here with you. This is an example problem, and we can pretty much go over that together. It would be also applied to the last one of the problems of the of your lab assignment. Okay, so in this example, there are a circuit as such is given, and we would like to pretty much use a voltmeter and an EVM to pretty much measure the V sub AB across this circuit between 2 points A and B. By inspection, we should be able to come up with that. We would come up with that as at 50 volts. Half of that, since they're pretty much of the same resistance, and as you can see, as such, it's 100 volts. So by inspection, we should pretty much be able to tell if it's 50 volts across point A and B. However, what if we would like to use an instrument to measure this? And we're using, again, two instruments. One is the voltmeter, the other one is an EVM. And we would like to see what would be the results and which one is more accurate. Let's take a look at using a voltmeter with the resistance of R sub I is 0.1. That's given. Again, as you can see, this is 0.1 actually given. This is 0.1. R sub I is 0.1. So the R sub AB, the inverse of R sub AB between point R and between the point A and B is actually 1 over R sub 2, which is 0.5, plus 1 over R sub I, which is 0.1. So as such, the R sub AB could be calculated. An inverse of 1 over R sub AB is calculated as such, and we pretty much use that. It's going to be 1 over 12, so 2/10, and then from here it's going to be 1/12. Okay, knowing R sub AB and the relations I between O and A and I between A and B. Again, if you look at this point, I between point O and A and B, it's the same. So using that equation, then we could easily pretty much plug in the numbers and come up with this equation in which V sub AB is E sub R sub AB divided by R sub AB plus R1. R1 is given as 0.5, excuse my French, plus 1/12. That's the R sub AB that we just calculate. And then the E multiplied by R sub AB. E is 100 given, and again 1/12. That's the R sub AB. So we're going to calculate V sub AB as 14.3 volt. That is very inaccurate. And knowing the theoretical values, compare 14.3 to 50, right? But that is pretty inaccurate because the error is like 71% the way we calculate. Now, how do we usually calculate an error? Again, the error is usually a deviation from certain value. In this case, we use the theoretical value of 50 volt. And we simply subtract, we simply compare the answer that we calculated, V sub AB as 14.3. We compare that with the theoretical value, and we come up with 71%. We simply subtract the value and divide it by the value that got subtracted from 14.3. So it's really minus 71.3. That means it's below our value. If it was over, then it's going to be plus 71%. If it was instead of 14.3, if it was much higher than 50, 71% higher than 50, then this would have been plus 71%. Now, for the second method, we use the EVM. R sub I is 17 given. Again, R1 and R2 is given. Note that the difference in R sub I, in that case, R sub I was 0.1. Now the R sub I would be 17. Okay, same units. I don't repeat the units throughout the problem. 1 over R sub AB is equivalent to 1 over 2. It equals to 1 over R sub 2 plus R sub I. As such, R sub AB would be 0.48571 for that same unit. And again, we use the same relations. V sub AB is going to be E sub R sub AB plus divided by R sub AB plus 1. And as you can see, the voltage would be 49.2753 volt. And this would be much more accurate. It is much more accurate. As you can see, the error is only minus 1.46. Again, this is 1.46% below the theoretical value that we calculated. Okay, that was one of the problem I wanted to go over with you guys. The bridge, we have discussed it already, but for the bridge, I can let me quickly go over that. The Wheatstone bridge, again, the Wheatstone bridge is pretty much it converts the measured signals to resistance signals. It's very important to realize that, and then often the changes in such resistance values are quite small, so it is pretty accurate. So we use Wheatstone bridge to perform such, calculating such a resistance. In this case, so we call it R sub X. Okay, so there are two conditions for this. One is the balanced and one is the unbalanced. So both of them have put down here, in which you can actually see how it is being calculated, the theoretical foundation behind. But it is really pretty straightforward, and for two of the lab questions, you would perform this. Again, make sure to refer to the book. There are examples. I don't see those examples are pretty straightforward forward, it's going to provide you with these equations, and let me know if you have any questions about that. Okay, so that brings me to the end of this lecture. If you have any questions, feel free to contact me. Thank you.